Usually when we discuss cloud infrastructure in the broader industry, there's this massive expectation of a single pane of glass.
Oh, the legendary single pane of glass.
Exactly. You boot up a dashboard in the morning, the system shows you a blinking red light, and the administrator simply clicks a button to execute the needful. It is presented as this straightforward binary operation.
Yeah, the server is either healthy or it is throwing an error. Very binary.
Right. But then you step into the actual reality of operating SAP Business Technology Platform, or SAP BTP, and suddenly you are dealing with deeply hybrid landscapes.
Absolutely. The complexity just multiplies exponentially.
I mean, you have on-premise legacy systems like SAP ERP Central Component or SAP S/4HANA talking through the SAP Cloud Connector to cloud-native microservices hosted in Cloud Foundry or Kyma.
And suddenly, in that specific environment, that beautiful single pane of glass completely shatters.
It shatters completely. We are looking at a diagnostic landscape that is highly layered, intensely distributed, and honestly, if you do not understand the underlying architecture, it is just quite murky.
It is the absolute definition of diagnostic muddy waters. I mean, if you lack a structured observability strategy, your engineering teams will spend weeks, literally weeks, just trying to locate the correct log file.
Oh wow, weeks just for a log file.
Easily, because the complexity stems from the fact that SAP BTP is not a monolith. You are integrating deeply customized ABA code with, modern containerized Node.js application.
Right, so when a business user complains that an application is slow, the latency could be anywhere. It could be residing in the front-end browser, the cloud router, the microservice execution.
A database query, or even the network tunnel connecting back to the on-premise landscape.
Right.
Without a highly structured approach to telemetry, you are essentially flying blind in a hurricane.
So let us unpack this architecture today, because we are completely bypassing the high-level fluff. If you are joining us for this deep dive, you are likely an SAP administrator, a DevOps engineer, or an enterprise architect who is actually in the trenches doing the needful.
Yes, this is for the practitioners, the people actually configuring the systems.
Exactly. We are going to build the ultimate observability control tower for SAP BTP. We will strictly distinguish between central and local observability tools, exploring the mechanisms behind SAP Cloud ALM, SAP Cloud Logging, and the SAP Alert Notification Service.
It is a massive stack to cover, but it is so crucial.
It really is. But before we start, provisioning tenants and writing configuration files, I like to frame this architecture using a specific analogy. Think of it as a control tower versus a mechanic's garage.
Oh, I like that. The control tower in the garage.
Right. Central observability, well, that is your air traffic control tower. The operators up there are looking at the entire airspace across multiple regions, spotting smoke on a runway from miles away.
But they cannot actually fix the plane from the tower.
Exactly. Because local observability, well, that is the mechanic on the ground, pulling the specific aircraft into the garage, opening up the engine cowl, and looking at the exact faulty valve. The control tower cannot fix the valve, and the mechanic cannot see the whole airspace.
That is a highly accurate representation of the separation of concerns that SAP has intentionally architected. To understand why we must build two separate layers of observability, we really have to look at the workload types running on SAP BTP.
Right, because it is not just one type of application.
No, not at all. We are fundamentally dealing with two different paradigms here. On one side, we have software as a service or SaaS applications. Think of SAP BuildWork Zone or SAP SuccessFactors.
Okay, so finished products, basically.
Precisely. Here, you are consuming a finished product. SAP manages the underlying infrastructure, the database, and the runtime. The telemetry you require here is strictly focused on availability, high-level performance metrics, and application health checks.
Because, you do not have access to, nor do you want to see, the underlying memory heap dumps of a SaaS application.
Yeah. Exactly, because you cannot do anything with a memory heap dump for a SaaS product anyway. You cannot patch SAP's proprietary backend code. It is out of scope.
That makes total sense. So that is SaaS.
But on the other side of the platform, you have platform as a service, or PaaS environments. This is where your developers are deploying custom code into the SAP BTP Cloud Foundry environment, the Kyma Kubernetes runtime, or the ABA environment.
And in PaaS, you are entirely responsible for the application logic.
Yes. The telemetry data required for POS is exponentially denser. You need deep dive metrics, garbage collection statistics, custom application logs, database connection, pool utilization, and distributed open telemetry traces.
So if we step back, the overarching strategy for you, the enterprise architect, is about harmonizing this massive, disparate influx of telemetry data.
It is a massive harmonization effort, yes.
We have to capture the high-level SaaS health checks and the low-level POS debug logs and utilize them to reduce two very specific critical operations metrics: mean time to detect, or MTTD, and mean time to resolve, or MTTR.
Yes, and this brings us to the golden architectural rule of SAP BTP observability. And honestly, if our listeners take away one fundamental concept today, it must be this.
Let us hear it.
Problem detection is strictly centralized to create a single source of truth, while problem resolution is decentralized, utilizing expert tools for specific domains.
You detect in the tower, you resolve in the garage.
Exactly that. Detect centrally, resolve locally.
Now, I have a major doubt regarding this philosophy. Let me push back on this split, because I hear this from back-end teams all the time.
Okay, go ahead.
If our overarching goal as an IT department is to reduce the mean time to resolve, why are we decentralizing the resolution?
I see where you're going with this.
Right. Think about the user experience of the operator. If I'm an operator sitting in the central control tower and I see a critical alert pop up, does it not drastically slow down my MTTR if I have to jump out of that central dashboard, authenticate into a completely separate local tool, and search for the context all over again?
It sounds like it would, yes.
Why not just, pipe all the raw logs directly into the central dashboard and give me everything in one screen, single pane of glass?
It is a valid doubt, and honestly, it is a trap that many organizations fall into when they attempt to build a homegrown observability stack.
They just pipe everything everywhere.
Exactly. But if we connect this to the bigger picture of enterprise hybrid landscapes, the reasoning for the split becomes crystal clear. Think about the sheer volume of telemetry generated by a custom microservices architecture.
It is gigabytes of data a day, sometimes terabytes.
Terabytes, easily. If you attempt to pipe every single debug level log line, every single raw distributed trace, and every minor CPU metric from every local subsystem directly into one central dashboard, you will completely overwhelm the ingestion engine.
The dashboard would just freeze.
It would crash. But more importantly, you will overwhelm the human operator. You will create severe, paralyzing ellipse fatigue.
Ah, I see. It is the classic signal-to-noise ratio problem. If the central tower is flooded with thousands of info-level logs stating that a pod scaled up successfully, they're going to completely miss the one fatal log stating that the database connection dropped.
Exactly. Centralizing detection prevents the noise from drowning out the actual crisis. The central tool is designed to correlate events and calculate business impact before an alert ever reaches the human operator.
So the tower only sees the smoke, not the everyday engine exhaust.
Right. However, resolution requires deep, raw context. You simply cannot debug a sophisticated memory leak in a Cloud Foundry application by looking at a high-level red or green business dashboard.
You need the exact logs.
You need the exact JSON-formatted log file from the specific millisecond the application crashed. So how do we solve the MTTR delay you mentioned? We rely on context passing.
Context passing, how does that work?
The SAP architecture seamlessly transfers the context from the central tool to the local tool. You do not start your search from scratch. You click a context-sensitive link embedded within the central alert.
Oh, so it acts as a bridge.
Exactly. And that link contains the correlation IDs, the timestamps, and the specific application GIs in its URL parameters. You land exactly on the relevant log lines in the local tool, bypassing the need to search entirely.
That makes perfect sense. The architecture handles the navigation, so the human operator does not lose those precious minutes during an outage.
It is all about efficiency.
So for you listening and mapping out your upgradation strategy, your primary action item today is to audit your current system landscape. You must identify exactly which workloads are running as SaaS versus PaaS.
That is step one, because this mapping dictates your next steps.
Right. For SaaS, you can largely rely on the out-of-the-box SAP metrics provided centrally. But for PaaS, you have to mandate that your developers instrument custom telemetry for local observability. If they do not write the code to emit the logs, the mechanic's garage will be empty when things break.
That is the crucial prerequisite. Once you have defined the boundaries of your landscape, we must architect the central observability engine itself.
And in the context of SAP, that central air traffic control tower is SAP Cloud ALM, or Application Lifecycle Management.
Yes. And we need to unpack SAP Cloud ALM because there are a lot of misconceptions about what it is.
Right, let us clear those up. First and foremost, Cloud ALM is itself a SaaS product built on SAP BTP. SAP handles the hosting, the patching, and the database maintenance. You do not need to install it on a virtual machine.
No infrastructure maintenance required on your end.
Exactly. And kindly note this crucial licensing fact, which is heavily emphasized in the official SAP architecture courses. All customers with an SAP Cloud subscription or a valid SAP Enterprise Support contract are entitled to provision and use SAP Cloud ALM at no additional cost.
It is already included in your entitlements. It is a massive value proposition.
Free central observability, essentially.
Basically, yes. But provisioning it is only the first step. We need to look under the hood at the core routing infrastructure inside SAP Cloud ALM.
Right, the intelligence of the tower.
Exactly. The true power of this platform comes from a proprietary engine called Intelligent Event Processing. Think of Intelligent Event Processing as the actual brain of the central tower.
The brain, what exactly is it processing?
It acts as the central ingestion point and the decision engine. It consumes an enormous volume of raw inbound data availability metrics, configuration items, log entries, and alerts forwarded from other localized infrastructures. And it parses that data to assign it to specific monitoring use cases.
Right, so we have this massive inbound flow of OData and REST APIs bringing telemetry in from across the globe.
Yes, and the Intelligent Event Processing engine intercepts these JSON payloads, looks at the event type, applies the predefined rules configured by the administrator, and then triggers an outbound flow.
The engine is essentially asking, does this metric breach a threshold? Does this log indicate a failure?
Precisely. And if the answer is yes, it executes an outbound action.
And that action could be what? Triggering a visual alert in an ALM dashboard.
It could be a visual alert, or initiating an automated remediation script, or even making an external API call to create an incident ticket in an IT service management tool like ServiceNow or Jira.
That is incredibly powerful. Automation right from the central brain.
Furthermore, when configuring Cloud ALM, we must strictly distinguish between features that are product-specific versus product-agnostic.
Okay, unpack that for me. Product-specific.
Well, SAP has engineered Cloud ALM with highly opinionated, pre-configured adapters for core SAP solutions. This is the product-specific content. If you connect SAP S/4HANA Cloud, SAP SuccessFactors, or SAP Ariba, Cloud ALM already knows exactly what a healthy system looks like.
Oh, wow. So it possesses out-of-the-box KPI definitions, default thresholds, and predefined alerting rules for those specific SAP data structures.
Exactly. You do not have to write the monitoring logic from scratch. It knows what a healthy S/4HANA system is supposed to be doing.
That saves months of implementation time. But, enterprise landscapes are not exclusively SAP.
Rarely are they strictly SAP, yes.
We have third-party databases, custom middleware, and external API gateways. What about them?
Which is exactly why Cloud ALM exposes open APIs for telemetry ingestion. This makes it product agnostic as well.
Ah, so you can format the telemetry from your non-SAP systems to match the ALM payload structure and p-post it to the intelligent event processing endpoints.
Exactly. This allows you to monitor external integrations side by side with your SAP landscape, achieving that true holistic central detection.
Now, I want to highlight a specific feature within Cloud ALM here because it fundamentally bridges the massive communication gap between the backend IT department and the business stakeholders.
Yes, business service management. It is a critical feature.
The feature is called Business Service Management. Strictly speaking, a business user, say the VP of Sales, does not care if a specific Cloud Foundry pod named Inventory Service Instance 3 restarts due to an out-of-memory error.
They do not speak that language at all. They just want the system to work.
Exactly. They only care if the order-to-cash business process is functioning. Business Service Management allows the enterprise architect to construct a logical abstraction layer.
You group all these underlying technical microservices, databases, and network gateways, and assign them to a single overarching business service.
It is a brilliant mechanism for calculating service-level agreements, or SLAs. The system utilizes a weighted dependency tree.
Right, so you can configure it so that if one underlying technical component fails, the business service status degrades slightly. But if a critical path component fails, the entire business service status flips to disrupted.
It translates highly technical telemetry-like CPU spikes or memory leaks into understandable status information, plotting it on an event calendar that business stakeholders can actually read.
It answers the fundamental question, is the IT issue impacting the business operation?
So your immediate mandate, if you are listening, is this. Verify your SAP Enterprise Support contract, log into the SAP For Me portal, and trigger the provisioning of your SAP Cloud ALM tenant today itself.
Yes, trigger it today. Do the needful.
And once it is provisioned, your very first architectural task is setting up those intelligent event processing rules to correlate the alerts you are already receiving.
That is the crucial first step.
Now, once you log into the Cloud ALM Launchpad, you will notice it is not just one giant confusing dashboard. It is a highly structured stack of specialized monitoring applications.
Yes, the ALM monitoring stack. We need to break down the stack, exploring exactly how these tools function and why you would deploy them.
Let us ground this in reality by introducing a scenario from the architecture modules. Let us talk about a hypothetical enterprise customer. Let us call them Rotating Banana.
Rotating Banana. It is an excellent case study. They are a massive, long-time SAP customer currently undergoing a major digital transformation.
Okay, so they are migrating.
Yes, they are transitioning their legacy ERP to SAP S/4HANA and simultaneously migrating custom workloads into the cloud. For our purposes, let us say Rotating Banana has deployed a highly complex custom cloud application in the SAP BTP Cloud Foundry environment.
Okay, what does this application do?
It is a partner portal where external vendors log in, check inventory in the backend S/4HANA system, and submit purchase orders.
Oh boy. So we have a custom Cloud Foundry React frontend, a Node.js middleware layer, an SAP HANA cloud database, and an SAP Cloud Connector tunneling back to the on-premise S/4HANA system.
It is the absolute definition of a hybrid diagnostic nightmare.
It really is. Let us explore the Cloud ALM monitoring stack by seeing how Rotating Banana would utilize each layer. Where do we start?
We must begin at the highest level of abstraction, business process monitoring.
Okay, business process monitoring.
This application within ALM is strictly intended for business process owners. You will not find technical KPIs like memory heap usage or network latency here.
So no CPU charts.
None. Instead, it focuses on end-to-end business process health to ensure continuity. For Rotating Banana, they would configure this to track the procure-to-pay process.
Got it. So it automatically detects anomalies in document flows. For instance, if purchase orders are being created, but the corresponding inbound deliveries are fundamentally delayed.
Exactly. You simply switch on the auto-discovery for relevant business process KPIs, and it begins tracking the business document lifecycle.
But when a business process anomaly is detected, the IT team still has to find the technical fault.
Right, which brings us to the next tool in the stack, integration and exception monitoring.
Integration and exception monitoring. This addresses the critical needs of the integration personas, right?
Yes, because modern landscapes like Rotating Bananas are deeply distributed. This tool provides end-to-end monitoring by correlating single messages across various cloud services.
The underlying mechanism here is fascinating. When a vendor submits a purchase order in the Cloud Foundry app, that payload has to travel through SAP Cloud Integration, perhaps pass through SAP Event Mesh, and finally hit the backend S/4HANA OData API.
Yes, and integration and exception monitoring tracks that specific payload across every single hop. It correlates the single message ID to the end-to-end flow.
So if the purchase order fails because the backend S/4HANA API threw a 500 internal server error, this tool catches the exception, highlights the exact integration flow step that failed, and shows you the error payload.
Exactly. You must configure this to track both your peer-to-peer interfaces and your orchestrated integrations.
Now, what happens when the vendors complain that the portal is just, slow?
The classic latency complaint.
Right. There are no hard errors, no crash pods, but clicking a button takes 15 seconds. This is where it gets really interesting for performance tuning. We must utilize real user monitoring, or RUMA, and synthetic user monitoring, or SUM.
Yes, RUM and SUM. Let us examine real user monitoring first.
Sure.
Real user monitoring is arguably the most powerful diagnostic tool for latency. It provides absolute transparency regarding the performance and errors actually experienced by your end users in production.
So real humans clicking real buttons.
Yes. Crucially, it measures latency at both the front-end browser level and the server-side processing level, allowing you to isolate the true root cause of UI lag.
Let me give you the exact data flow of how this works for Rotating Banana. A vendor in London clicks the Submit Order button on the React front end. Real user monitoring tracks that specific user call trace.
And it measures everything.
Everything. It measures the milliseconds it takes for the browser to render the DOM. Then it attaches a unique correlation header to the HTTP request as it leaves the front end. It tracks the network transit time.
It watches the requests hit the custom Node.js service calls on the BTP paste layer, measures the backend execution time.
Follows the call all the way into the SAP ANA database, measures the SQL query execution time, and tracks the response all the way back. It proves with mathematical certainty exactly where the latency lives.
You no longer have network teams pointing fingers at database teams. RUM gives you the incontrovertible truth.
It completely eliminates the guesswork. But real user monitoring is inherently reactive. It only generates data when a user is actively suffering through a slow application.
Yes, which is terrible for the user experience. To prevent the suffering entirely, we must implement the next tool in the stack: synthetic user monitoring.
Proactive observability.
This is a proactive approach to observability, yes.
Synthetic user monitoring is essentially building an army of robot users. To implement this, your QA automation team writes custom Selenium-based scripts.
Right, and you deploy these scripts to run 24 hours a day, 7 days a week, on remote Selenium WebDriver infrastructures hosted in various geographic regions.
These scripts simulate exact user behavior. The robot logs into the portal, clicks the inventory tab, fills out a purchase order, clicks submit, and measures the response time of every single action.
The architectural beauty of synthetic user monitoring is that it relies on identical, repeatable user scenarios executed at regular intervals. Because the variables are controlled, you get highly comparable performance metrics over time.
So if the backend database patch applied at 2.0 a.m. degrades performance by 400 milliseconds, the SUM robot detects it at 2.05 a.m.
Exactly. It triggers the alert via intelligent event processing, and the backend team can execute a rollback before the actual human vendors log in at 8.0 a.m.
It fundamentally transforms your IT operations from reactive firefighting to proactive optimization. That is incredible.
Moving down the ALM stack, we find Job and automation monitoring.
Right, background jobs.
Yes, in any enterprise landscape, there is a massive amount of asynchronous background processing happening. For rotating banana, they might have robotic process automation or RPA bots built with SAP build process automation running overnight to reconcile invoices.
They also have background jobs scheduled in their ABAP environments to clean up temporary database tables. Job and automation monitoring provides a centralized view of execution status, start delays, and runtime durations for these background tasks.
If a critical overnight batch job hangs and fails to complete, this tool raises the red flag before the morning shift begins.
Next, we must consider compliance and governance. This is handled by configuration and security analysis.
Think of this application as your automated compliance watchdog.
Because enterprise landscapes suffer from configuration drift constantly.
Constantly. A developer might manually change a parameter in a production environment to temporarily fix a bug and just forget to revert it back.
It happens all the time. This tool regularly collects configuration items and software component versions from connected systems and stores them in the Configuration and Change Database, or CCDB.
It is essentially doing a continuous diff check. You establish a baseline 2B state, for instance, mandating that all ABX systems must have a specific security parameter set to true.
The tool continuously runs a change analysis, comparing the ASIS reality of your systems against that baseline. If a parameter drifts out of compliance, it flags the violation immediately.
Finally, we reach the foundation of the stack: health monitoring.
The bedrock of technical metrics.
It is designed for lightweight, high-level system monitoring. You utilize health monitoring to execute application health checks for SaaS services, monitor the CPU and memory utilization of your SAP ABAP systems, and pull aggregated technical metrics from your custom BTP applications.
It provides the overall pulse of the landscape.
Okay, we have our control tower fully built, Cloud ALM is configured, intelligent event processing is routing our data, the monitoring stack is deployed.
Now, let us return to rotating banana and explore a catastrophic, real-world, local observability scenario.
Yes, let us break the system.
Rotating Banana's vendor portal is live in the SAP BTP Cloud Foundry environment. But suddenly, there is a major problem. The custom application randomly becomes unstable.
Unstable how?
It is dropping active vendor sessions, throwing intermittent HTTP 502 bad gateway errors, and to make matters worse, no central alerts were initially triggered in Cloud ALM.
Wait, no central alerts. Why?
Because the application is technically still running, So the basic health monitoring sauce checks are returning green, but the internal application state is failing. The central tower completely missed the smoke.
Ah, I see. The underlying container is alive, but the code logic is failing. The DevOps team has to step in, find the root cause, and fix this utilizing local observability tools.
This scenario perfectly illustrates the absolute necessity of the DevOps triad for local observability in SAP BTP. The central tower is not enough on its own. You need the mechanic's garage.
You need the garage, yes. The local observability triad consists of three deeply integrated tools. First, the SAP Alert Notification Service, which acts as the local net to capture critical events.
Second, SAP Cloud Logging, which provides the highly indexed, search-optimized environment for raw root cause analysis.
And third, SAP Automation Pilot, which is the engine used for automated remediation. We must analyze exactly how this interaction plays out during an outage.
Let us trace the architecture of the crash. Rotating Banana's custom Node.js application in Cloud Foundry suffers a severe memory leak due to an unoptimized database query.
The container runs out of memory, and the Cloud Foundry Diego cell forcefully terminates and restarts the container. This happens in milliseconds.
Right. And the SAP Alert Notification Service, which is instantiated locally within the same BTP subaccount as the application, is deeply integrated with the Cloud Foundry runtime. It catches that app crashed event instantly.
Now, because the enterprise architect has configured the integration properly, the alert notification service does not just sit on this event.
It formats a JSON payload containing the app name, the space GUID, and the crash timestamp, and forwards this critical event outbound to the central intelligent event processing engine in SAP Cloud ALM.
Cloud ALM receives it, processes the rule, and triggers a critical visual alert for the central support engineer on the dashboard.
But wait, let us pause here because this architecture usually sparks a fundamental doubt among engineers.
Okay, what is the doubt?
We stated earlier that we strictly separate local and central tools to prevent overwhelming the central dashboard. If the SAP Alert Notification Service is strictly a local observability tool sitting in the BTP subaccount, why is it sending payloads up to Cloud ALM, the central tool?
Ah, I understand.
Are we not violating our own architectural rule and risking alert fatigue?
It is a brilliant question, and the answer lies in the configuration capabilities of the alert notification service. It is not a blind forwarder. It acts as a highly intelligent local sieve.
A local sieve, so it filters.
Exactly. The local DevOps team configures strict conditions and rejects filters within the service. The custom application might be generating 5,000 INFO level log lines per minute, things like user authenticated or database query executed.
The alert notification service ignores all of that. It filters out the noise locally. It only propagates critical, predefined events, specifically the fatal crash events or out-of-memory exceptions, to the central tool.
Exactly. It curates the data feed at the edge. It only sends the smoke signal to the tower when there is actual fire on the runway.
So the central support engineer sees the critical alert in Cloud ALM. They see the metadata indicating that the rotating banana vendor portal has crashed in Cloud Foundry. But, as we established, they cannot fix a memory leak from a high-level dashboard.
No, they cannot. This is where the context-sensitive navigation we discussed earlier becomes paramount.
Right, the magical link.
The engineer clicks the context link embedded in the Cloud ALM alert. The architecture seamlessly routes them directly into the SAP Cloud Logging Service dashboard.
The context is passed via the URL, so when the OpenSearch dashboard loads, it is already filtered. The engineer does not have to search for the app name or the time range.
They land exactly on the raw JSON logs generated by the application at the specific millisecond of the crash. They can instantly read the exact stack trace, see the unhandled promise rejection, and identify the out-of-memory exception in the raw logs.
The MTTR is drastically reduced because the context mapping eliminated the search phase.
The root cause is identified rapidly. But to solve rotating bananas issue, you, the listener, must actually know how to provision, govern, and configure the SAP Cloud Logging Service.
It is a highly complex component. We are going to treat this next phase as a strict, step-by-step architectural tutorial. Setting up cloud logging requires rigorous planning.
You do not just navigate to the BTP cockpit and click Provision. As a BTP administrator, you must execute the planning phase, defining your local observability goals.
There are 4 critical architectural aspects you must evaluate before touching the provisioning button. Let us break down phase 1 of the configuration strategy. Step 1 is defining the scope.
You have to ask the business which workloads actually require deep, costly telemetry observation. Are you emitting high-fidelity signals from the development environment, the quality assurance environment, or strictly the production environment?
Storing terabytes of debug logs from a dev environment might bankrupt your BTP credits. You must define what needs monitoring to define your overarching administrative goals.
Step 2 involves legal and authorization constraints. This is heavily dependent on data sovereignty laws, such as GDPR in Europe.
Because application logs often inadvertently capture personal identifiable information, or PII.
Exactly. You must evaluate if you have compliance requirements that mandate observability data must reside in a specific geographic region. If so, you cannot use a globally shared logging instance. You must provision separate, isolated instances of cloud logging in specific regional data centers.
But let us say you are allowed to use a shared instance to save on compute costs. You have multiple development teams sharing one cloud logging tenant. You face a massive security risk. Team A should not be able to read Team B's application logs, especially if Team B is processing financial data.
Therefore, you must configure index-level or document-level security.
How do you do this? You map roles from the SAP Identity Authentication Service, or IAS. You configure OpenSearch to recognize specific IAS group claims, ensuring that when a developer authenticates, the database dynamically restricts their query results to only the indices they are authorized to view.
Step 3 is sizing for ingestion and storage. Cloud logging is not an infinite black hole. You pay for what you use.
You must calculate the volume of data your microservices will ingest per day and how many days you are legally required to retain that data in hot versus cold storage.
Your mandatory action here is to navigate to the official SAP Cloud Logging Capacity Unit Estimator tool. You input your expected payload sizes and retention periods. The tool will output your required capacity units, which dictates your service plan.
Crucially, you must configure the auto-scaling limits for the ingest and storage components in your deployment descriptor to prevent unexpected billing spikes during a log storm.
And step 4 of the planning phase is defining your operations and tenancy model. Will you implement a centralized instance sharing model among multiple teams?
This significantly lowers infrastructure costs but requires the complex access governance and IAS mapping we just discussed. Or will you mandate isolated team instances where every microservice team gets their own dedicated cloud logging database?
That is much easier to govern, as the blast radius is contained, but the financial cost multiplies rapidly. You must make this architectural decision upfront.
Let us assume you have made these decisions, opting for a shared instance with strict index-level security. We move to the technical setup phase.
Kindly note the sequence of these steps, as execution out of order will result in a failed deployment.
The first, and arguably most complex prerequisite, is configuring the identity provider. You must set up the underlying SAP Identity Authentication Service and create the corresponding authentication application.
You define your user groups, for example, rotating Banana Logs admin, and assign the appropriate administrative users within SAP IAS.
Then, we move to provisioning the service itself. You log into the SAP BTP cockpit, navigate to the specific sub-account, open the service marketplace, and provision your SAP Cloud Logging instance using the parameters calculated from the capacity estimator.
Now, here is a critical technical detail where many architects fail. You must establish the trust configuration. Ensure that your security assertion markup language, or SAML configuration in the cloud logging instance, perfectly matches the setup in your identity service.
This is a vital point of failure. When a user logs in, IAS sends a SAML XML payload containing claims about the user.
If the group's attribute in that SAML assertion is mapped incorrectly in the cloud logging role collection, the developer will successfully authenticate via single sign-on, but they will receive a 403 forbidden error from the database because their permissions cannot be validated.
They will be locked out of the logs entirely. You must ensure the SAML attribute mapping is pristine.
Once the infrastructure is provisioned and secured, we reach the final step: binding the applications.
The developers or workload owners must bind their BTP applications to the newly provisioned cloud logging service instance so data can flow. To ingest logs, metrics, and distributed traces reliably, SAP strongly recommends utilizing the OpenTelemetry standard protocol.
OpenTelemetry, or OTel, is an open-source observability framework, and it has become the absolute industry standard. Let us ground this with an illustrative example directly from the SAP BTP Developer Guide.
Assume a developer at Rotating Banana is building their back-end middleware using the Cloud Application Programming Model, or CAP, utilizing Node.js.
To emit high-fidelity signals from their FIP app running on Cloud Foundry to the cloud logging ingestion APIs, they do not write custom HTTP POST requests.
No, they utilize the framework. They follow the specific mission outlined in the guide titled Implement Observability in a Full-Stack CAS Application following SAP BTP Developer's Guide.
They bind the application to the cloud logging service via the BTP service broker. Then they configure the OpenTelemetry exporters within their package.json file or via environment variables.
The CAP framework natively understands these OTel configurations. Suddenly, without writing custom logging code, rich, structured JSON payloads containing distributed trace IDs, memory metrics, and application logs start flowing over the OTLP protocol directly into the cloud logging analytical dashboards.
The profound architectural advantage of SAP Cloud Logging is that it offers dedicated, out-of-the-box support and pre-built OpenSearch dashboards for SAP BTP runtimes like Cloud Foundry and Kaima. The dashboards instantly visualize the OpenTelemetry data.
However, because it relies on generic, industry-standard ingestion APIs like OTLP, you can ingest telemetry from arbitrary non-SAP sources as well.
If you have an external AWS Lambda function participating in the business process, it can also emit OpenTelemetry traces directly to SAP Cloud Logging, unifying the local observability layer.
Okay, let us trace our steps back. Rotating Banana's application crashed. We detected the bug centrally in Cloud ALM via the alert notification service. We seamlessly routed to Cloud Logging, queried the OpenTelemetry traces, and found the unoptimized database query causing the memory leak.
The developer pushes a code patch to fix the leak. But in an enterprise environment, deploying a patch can take days due to change advisory board approvals.
How do we ensure the operations team is not woken up at 3:00 a.m. if the memory leak happens again before the patch is fully deployed to production? We must take the human out of the loop.
This brings us to the final piece of the architecture, closing the loop with automation.
We rely on the third pillar of our local observability triad, SAP Automation Pilot. Furthermore, we must couple this with robust external API management. Modern ALM toolchains must connect diverse teams relying on diverse technologies.
The central control tower cannot exist in a vacuum. SAP Cloud ALM offers open APIs specifically designed to expose events and trigger actions in third-party systems.
So we can configure an outbound webhook from Cloud ALM's intelligent event processing engine. When the alert fires, ALM makes a REST API call directly into ServiceNow.
It passes the JSON payload containing the error details, the affected system, and the timestamps, and automatically generates an incident ticket with all the context attached.
The human support desk does not have to manually copy and paste information. But we can go a step further than just ticketing. We can trigger an actual operation flow to fix the system automatically using SAP Automation Pilot.
Precisely. SAP Automation Pilot is a low-code automation engine designed to execute operational tasks in BTP. Let us walk through the automated remediation flow.
If the cloud logging service detects that the Rotating Banana app is reaching 95% memory utilization, indicating an imminent crash, it forwards that event to Cloud ALM. Cloud ALM triggers an outbound event. Automation Pilot catches that event payload.
An Automation Pilot parses the JSON, extracts the specific Cloud Foundry application ID, authenticates against the Cloud Foundry Controller API utilizing a secure service broker credential, and automatically executes a predefined declarative script.
That script issues a command to forcefully restart the specific Cloud Foundry pod, or perhaps dynamically scale up the memory allocation from 1 GB to 2 GB. It reverts the system to a healthy state entirely without human intervention.
That is the holy grail of cloud operations. A self-healing, automated remediation architecture. The system detects the anomaly, logs the evidence, alerts the necessary dashboards, and executes the temporary fix before the end user ever experiences a 502 bad gateway error.
Now, we have covered a massive amount of architectural ground today, delving deeply into the mechanics of both central and local observability. In my experience, even seasoned SAP architects can get confused by the sheer number of acronyms and overlapping capabilities.
It happens to the best of us. There's a lot to track.
So we are going to validate this knowledge. We are going to integrate a peer-reviewed debate based exactly on the official course assessment found in the source material. Listeners, consider these architectural dilemmas and see if you can identify the correct strategy before the expert breaks it down.
I am ready. Let us test the architectural comprehension.
Here's a scenario I encounter frequently. I had a junior DevOps engineer approach me during a deployment. They were experiencing application crashes in the Kaima runtime, and they confidently told me they were going to use the SAP BTP cockpit as their primary tool to perform the local root cause analysis. They assumed the cockpit was the central hub for everything. I had to stop them immediately. Why is that a critical mistake? Out of the SAP Cloud Logging Service, SAP Automation Pilot, and the SAP BTP Cockpit, which is fundamentally not a local observability tool.
The fundamental mistake is relying on the SAP BTP cockpit for telemetry. The correct answer is the SAP BTP cockpit is not an observability tool at all.
Right, it is strictly administrative.
The cockpit is strictly a central management and administration user interface. You utilize it for managing global account hierarchies, configuring service entitlements, assigning role collections, and establishing trust configurations with identity providers.
It is absolutely not designed as a telemetry analysis tool. You cannot query an OpenTelemetry trace, view raw application logs, or execute remediation scripts within the BTP cockpit.
Cloud Logging and Automation Pilot, however, are dedicated local operations tools purpose-built for those exact tasks.
Spot on. It is an administrative tool, not a diagnostic one. Next dilemma. We discussed the massive inbound flow of telemetry data into the central control tower.
Yes.
A colleague asked me how exactly the system decides whether an incoming log should trigger a dashboard warning or send an API call to ServiceNow. What is the specific mechanism enabling this problem routing in SAP Cloud ALM? Is it handled by the integration and exception monitoring application? Or is it handled by the Intelligent Event Processing Engine?
It is entirely handled by the Intelligent Event Processing Engine. Integration and exception monitoring is merely one of the specialized applications within the stack. It visualizes the data.
Right. Visualization versus routing.
Exactly. Intelligent Event Processing is the underlying core routing infrastructure. It is the central brain that intercepts the raw JSON payloads, evaluates the predefined conditional rules, correlates events across different systems to prevent alert storms, and ultimately triggers the automated alerts or outbound API calls.
Exactly. The brain routes the data, the applications display it. Now, regarding the telemetry itself, when we mandate that our developers instrument their custom BTP Cloud Foundry applications so that they emit structured logs, metrics, and traces back to our observability tools, what is the required mechanism or protocol we must enforce?
This is an important one.
Are we asking them to implement the legacy SAP passport mechanism, or are we mandating the OpenTelemetry standard?
For modern custom applications built on BTP, you must mandate the OpenTelemetry standard. SAP Passport was an older proprietary mechanism used primarily for tracing requests across traditional SAP ABAP landscapes.
But for cloud-native microservices running in Cloud Foundry or Kyma, OpenTelemetry is the absolute industry standard protocol.
It dictates exactly how the distributed trace IDs are generated, how spans are structured, and how the OTLP payload is formatted when it is emitted to the ingestion APIs of SAP Cloud Logging.
Perfect. Final overarching architectural check. We have discussed a myriad of tools today. If an auditor asks you to point to the single, overarching central observability tool for the entire SAP BTP landscape, the single source of truth for problem detection, which tool is it?
The final boss question.
Is it SAP for me, the SAP BTP Cockpit, SAP Cloud Logging, or SAP Cloud ALM?
The central observability tool is unequivocally SAP Cloud ALM. Cloud logging is strictly local for deep dive resolution. The cockpit is for administration. SAP for me is a customer portal for licenses and support tickets.
SAP Cloud ALM provides the centralized air traffic control tower, delivering that single source of truth for problem detection across your entire hybrid landscape.
Understanding these strict architectural boundaries between local and central tools and the protocols binding them together is absolutely critical. It is not just required for passing SAP certification exams, it is the fundamental prerequisite for architecting a resilient, scalable enterprise operations strategy.
Let us summarize the intensive journey we have undertaken today. We started by aligning our overarching strategy, recognizing the absolute necessity to split our operations into centralized detection and decentralized resolution to combat alert fatigue.
We built our central control tower using the Intelligent Event Processing Engine within SAP Cloud ALM, ensuring we deployed the appropriate monitoring stack.
Leveraging real user monitoring to track UI lag, synthetic user monitoring for proactive health checks, and business service management to translate technical failures into business SLAs.
And then we tackled the reality of system failure. When the custom rotating banana application crashed, we utilized the SAP Alert Notification Service as a local sieve to forward only the critical crash event.
We decentralized our resolution, leveraging context-sensitive navigation to jump seamlessly into SAP Cloud Logging, bypassing the search phase to perform deep dive root cause analysis using structured OpenTelemetry data.
Finally, we automated the temporary remediation utilizing SAP Automation Pilot integrated via outbound webhooks.
It is a comprehensive, meticulously engineered closed-loop system. We detect centrally, analyze locally, and remediate automatically. When executed properly, this architecture dramatically reduces your mean time to resolve and fundamentally stabilizes your hybrid enterprise landscape.
It completely changes how IT operates.
But before we sign off, I want to leave you with a final, highly provocative thought to consider. The official source texts briefly mention the future roadmap and vision for SAP Cloud ALM's intelligence capabilities. It states that SAP is planning to provide SAP automation pilot scripts that are actively supported by generative AI.
That represents a profound evolution in systems architecture. We are talking about large language models integrated directly into the operations toolchain.
Think deeply about the implications of that for your current tech stack. Right now, a human architect has to manually write the declarative script in Automation Pilot to restart a pod or clear a database cache.
But if an observability tool can not only detect an anomaly, but leverage generative AI to analyze the raw OpenTelemetry logs, dynamically write a custom, highly specific remediation script on the fly, and execute it, are we moving away from the concept of observability entirely?
Are we entering an era of truly autonomous, self-healing enterprise architecture? How will your role as a senior SAP administrator or enterprise architect fundamentally change when the system literally debugs, patches, and stabilizes itself while you are sleeping?
It forces a complete paradigm shift. It forces us to reconsider the actual value we add as IT operators. If the mechanics garage becomes fully automated by AI agents, the human enterprise architect must elevate their focus entirely.
You will no longer debug code. You will focus purely on optimizing the strategic design of the control tower, governing the AI permissions, and ensuring the efficiency of the overarching business system flow.
It is a fascinating horizon and something vital to mull over as you architect and deploy your next massive SAP application.
Thank you for joining us on this exhaustive deep dive into SAP BTP Observability Architecture. Do not just listen and move on. Log into your SAP BTP trial or production environment today itself. Map your hybrid landscape, evaluate your telemetry streams, and execute the strict actionable configuration steps we discussed. Keep building resilient systems, keep observing your telemetry, and we will catch you on the next deep dive.